In this video, we're going to learn one of the most important techniques in Calculus 2, integration by parts. Up to this point, we've learned substitution, but substitution doesn't work for every integral. Sometimes our integrand is the product of two different kinds of functions, and neither substitution nor the basic integration formulas help. That's exactly where integration by parts becomes useful. I'm going to teach you how to know when to use this method, the formula that you'll need to use, and the steps you can follow, and then we'll work through 6 examples, probably very similar to the examples that you'll need to know how to solve. And then finally, we're going to learn about tabular integration. It's a method that can save you a lot of work. Let's get started. The hardest part about integration by parts is usually not applying the formula. It's recognizing when you need to use the method. You can use this method when you're integrating two functions, and one function can be integrated repeatedly until it becomes 0, such as the x in this integral and the x in this integral, while the other function can be integrated repeatedly. That other function would be something like e to the x or sine x. You can also use integration by parts when differentiating one function, such as ln x or arctan x, simplifies the integrand, and the other function, in this case it's just dx, can be integrated repeatedly. Remember, the integral of dx is just x. You can also use integration by parts when the original integrand, such as e to the x cosine x, reappears after repeated use of integration by parts. We're going to go over all of these examples in just a few minutes, but we first need to go over the formula that we'll need to use. We're now going to go over the integration by parts formula that you'll need to know and the steps that you can follow when solving an integral using this method. The integration by parts formula looks like this. You're going to use it when you're integrating two functions and you set one equal to u right here, and then the other one you're going to set equal to dv. And sometimes that other function might just be dx. The formula is uv minus the integral of v du. I want to show you real quick where this formula comes from so it doesn't feel like I'm just pulling it out of a hat. It actually comes from the product rule. We let u be the function f of x, and we're going to let v be the function g of x. We then use the product rule, that's right here, the derivative with respect to x of f times g, and we get that expression on the right. Then what we're going to do is we're going to integrate both sides of the equation. We have the integral of a derivative, so we get back f of x times g of x and this formula on the right-hand side. Now all we need to do is put this back in terms of u and v. F is u, g is v, and that gives us this formula on the right-hand side. Now we just have to solve for the integral of u dv, and out pops our integration by parts formula. You can compare that back up here to the top and see that that's exactly our formula. Now that we know the formula that we need to use, let's go over the 3 steps that you can follow when integrating using integration by parts. Step 1 is by far the hardest. And in step 1, we are going to choose u to be the function that can be differentiated repeatedly until it becomes 0. An example of this would be the x in this integral x e to the x dx. Or we can choose u to be the function that becomes simpler when differentiated. An example of this would be if we're trying to integrate natural log x, and we'll set natural log x equal to u, and then just remember that the derivative of that is 1 over x, so it becomes algebraic, and that's considered simpler. Let's also note that dv is the part that remains. So in our first example, dv would be e to the x dx, and in our second example, dv is just dx. Looking over here on the right-hand side, the acronym ILATE is just a shortcut for this same idea for choosing u. The functions here that you can choose to be equal to u, either inverse, logarithmic, algebraic, trigonometric, or exponential, are listed roughly in the order that they simplify when differentiated. The exception to this is that when both factors are equally low in the list, such as a trigonometric like cosine x and an exponential like e to the x, this shortcut doesn't help and we have to do something different. I'll show you what to do for a problem like that when we go through our examples. Let's now look at steps 2 and 3. They are much easier. Step 2 is to just set up and fill in the following table. You choose u and then take its derivative, and then the part that isn't u is your dv, and you integrate that part. And then in step 3, you just apply the formula. The integral of u dv is equal to uv minus the integral of v du. When I implement this formula, I usually use arrows. Let me show you what that looks like. You multiply u times v, so I make an arrow that looks like this, and then you subtract v du, so to indicate the subtraction, I put an arrow that goes like that to the left. And that just helps me remember the formula. Let's now look at some examples. We're going to go over 6 examples where we are going to use integration by parts to evaluate the integral. To make things easier, I've placed the integration by parts formula right up here. We're going to start by setting our integral equal to the integral of u dv, and that way we can easily use the formula. So let's let this equal the integral of u dv. Now we'll decide what part of the integrand is equal to u and what part we'll set equal to dv. If possible, we want to choose u to be the function that can be differentiated repeatedly until it becomes 0. Looking at our integrand, that function is equal to x. So let's let u be equal to x, and then the part that is left over, e to the x dx, that becomes our dv. On the left-hand side, we're going to take the derivative. The derivative of x is just dx. And then on our right-hand side, we are going to integrate. So this is going to be the integral of e to the x dx. And that is equal to e to the x. We'll add the plus c when we're all done. This gives us the integral of x e to the x dx is equal to u times v. That's these two terms multiplied. So that is x e to the x. And then we're going to subtract off the integral of v times du. So I always make my arrow like this. And that helps me remember that we're subtracting. And v times du is e to the x dx. So we integrate this once more. So this is x e to the x minus the integral of e to the x. So that's just e to the x. Now we add our arbitrary constant c. One thing that we need to do is notice that there is an e to the x common to each term. So we want to factor that out. And this leaves us with the answer x minus 1 quantity times e to the x plus our arbitrary constant. And there's our final answer. Example 2 is very similar to example 1, and you may want to pause the video and see if you can work through this problem on your own. We're going to begin by setting our integral equal to the integral of u dv, and then we'll know that that is equal to uv minus the integral v du. We need to start by choosing u, and we want to choose it to be the function that we can differentiate repeatedly until it becomes 0. And that function is equal to x. So u is equal to x, and then our dv is going to be whatever's left over, and that is equal to sine x dx. We differentiate u, so that gives us du is equal to dx. And then on the right-hand side, we're going to integrate. So we have the integral sine x dx. That will be our v. And this is minus cosine x. Now we know that the integral of x sine x dx is our u times v minus our integral v du. Here's our u times our v, and that gives us a minus x cosine x, and then we're going to subtract v times du, and we're going to integrate that. So we have a minus the integral minus cosine x dx. Before we integrate, let's go ahead and let's combine those negatives. So we have minus x cosine x plus the integral cosine x dx. We can now integrate that. So we have minus x cosine x. The integral of cosine is sine x. So we have plus sine x. Now we have to add on our arbitrary constant. And there's our final answer. Let's now move on to example 3. This example is very different from the first two. It's one where we're going to need to use integration by parts twice. We're integrating x squared e to the x dx, and we're going to set this equal to the integral of u dv, and then writing our formula, that is uv minus the integral v du. I always tell students that if you write that formula every time, it will help you memorize it. We're going to start by choosing u. If possible, we want to choose u to be the function that when differentiated, it eventually becomes 0. And that function, in this example, is going to be x squared. So u is x squared, and then dv is whatever is left. In this case, that is e to the x dx. On our left-hand side, we're going to differentiate. So du is 2x dx. And on our right, we're going to integrate. Once you get used to this, you don't have to write that integration sign. And this is just e to the x. Now we're going to apply our formula. The integral x squared e to the x dx is equal to uv minus the integral v du. We'll multiply u times v. That gives us x squared e to the x, and then we'll subtract v times du. So we're going to subtract the integral 2x e to the x dx. Let's rewrite this, and we're going to pull out the 2. So this becomes x squared e to the x minus 2 times the integral of x e to the x dx. Now we're going to have to use integration by parts again. We're going to let u be equal to x, and then our dv is what's left over. So we're going to let u be equal to x, dv be equal to e to the x dx. This gives us du is equal to dx, and then v is the integral, and that's just going to be e to the x. Now let's come way back over here to the left, and let's write down our answer. We had an x squared e to the x, and then we had a minus 2. Now we're going to do our multiplication. We're going to multiply u times v. So that's x e to the x, and then we're going to subtract off the integral of v times du, and that is just e to the x dx. That's a nice one to integrate. Let's go ahead and do that. This gives us x squared e to the x. I'm going to go ahead and carry through the 2 at the same time. Minus 2x e to the x. Minus 2 times minus 1 is plus 2. And then our integral is e to the x. and we add on our constant. We're almost done, but we need to rewrite our answer so it's in a better form. Notice that there is an e to the x that is common to each term, so we can pull that out, and we end up with x squared minus 2x plus 2 all times e to the x plus c. And there's our final answer. At the end of this video, I am going to show you an easier way to do this type of problem. This next example falls into the category of choosing u to be the function that becomes simpler. In this case, it becomes algebraic when you differentiate it. And that function that we're going to choose to be u is equal to ln x. I actually had this problem on an exam that I took in high school. And I can remember sitting there staring at this problem for 10 minutes and having no idea how to solve it. So hopefully that won't happen to you after you see this. We're going to let u be natural log of x, and then dv is what's left over, and in this case, that's just dx, and that's just fine. Now we're going to differentiate the left-hand side. The derivative of natural log x is 1 over x dx. And then we're going to integrate the right-hand side. The integral of dx is just x. Our integral, natural log of x dx, looking up here at the right, is equal to uv minus the integral v du. We're going to multiply u times v, so that is x ln x, and then we're going to subtract off the integral of v times du. So we have minus the integral v, which is x, and then du is 1 over x dx. So this is x ln x minus the integral dx, and this is just equal to x ln x minus x plus our arbitrary constant. And then at the very end, we can pull out an x, and we have ln x minus 1 plus c. And there's our answer. Just like with so many other problems in Calculus 2, the procedure is really not that hard. The hard part is trying to figure out how to solve the problem. And honestly, that just comes from practice. I made sure to include this example because it also falls into the category of choosing u to be the function that becomes simpler when you differentiate it. Not go to 0, but becomes simpler. And I also wanted to include this because it's a definite integral. And I just want to show you how to do that when you're using integration by parts. Let's start by choosing u. We're going to choose u to be arctan x. You may recognize this function as inverse tan x. It's written both ways. And then dv is what's left over, and in this case, that is dx. On the left-hand side, we are going to differentiate. The derivative of arctan x, if you remember, is 1 divided by 1 plus x squared, and then we have our dx there. And then on the right-hand side, we're going to integrate dx, and that just gives us x. Let's put aside the definite integral for a minute, and let's just solve the indefinite integral. So we're going to solve the indefinite integral arctan x dx, and we'll use our integration by parts formula. This is uv minus the integral v du, and remember that this part is just our integral u dv. Let's multiply u times v. That gives us x arctan x, and then we're going to subtract off the integral of v times du. Our v is x, and then our du is 1 over 1 plus x squared dx. Now, we're not out of the woods yet. We need to integrate this integral right here. You might recognize that we can integrate this by using u substitution. We're going to let u be 1 plus x squared, and then du is equal to 2x dx. I'm going to come over here to the left. This gives us x arc tan x. That just comes along for the ride. And then we subtract off the integral. X dx, that's right here, is going to be du divided by 2. And then 1 plus x squared is just u. So this is x arc tan x minus 1/2 the integral 1 over u du. I'm writing it like that so that you can recognize that integral. That integral is the natural log function. So this is x arc tan x minus 1/2 natural log, don't forget the absolute value, u plus c. Now let's go ahead and let's plug back in what u is. So this is x arc tan x minus 1/2 natural log. Now, let's go back up here to the right-hand side at the top. There's our u. Notice that it's 1 plus x squared, so it's always going to be positive. So we can drop the absolute value sign. And this becomes 1 plus x squared. And then we'll put our plus c there, but in a second here, we're going to get rid of that. What we're going to do is go back to the definite integral. We were asked to solve the integral from 0 to 1, arc tan x dx. So now we're going to write down exactly what we just got. Let me highlight that in blue here. That's this part right here. And we're going to evaluate that from 0 to 1. So this becomes x arc tan x minus 1/2 natural log 1 plus x squared. And then our x is going to go from 0 to 1. And our plus c goes away. So let's plug in first that x is 1. So this becomes arc tan 1 minus 1/2 natural log 1 plus 1 is 2, so that's natural log 2. Then we subtract off our lower limit. X is 0, so our first term is 0. And then we have a minus 1/2 natural log of 1. Natural log of 1, that goes to 0. So we're just left with our first two terms. And our answer is arc tan 1. To find that answer, you have to think about what angle. Remember, an arctangent is always an angle. For what angle is the tangent 1? And that's pi over 4. So this becomes pi over 4 minus 1/2 natural log 2. And that's our final answer. This last example is a classic integration by parts example. It's one where you have to use integration by parts 2 times, and then you get back the original integral, and you have to solve for it. You just have to learn to recognize that the technique that you can use to evaluate this integral is integration by parts. So we're going to set this equal to u dv, and we're going to start by choosing u. With many integration by parts examples, you always choose u to be the function that you can differentiate to eventually become 0, or that you can differentiate and it becomes more simple. Neither of those work here. So for this example, we can choose u to be either e to the x or cosine x. It doesn't matter which one. I'm going to choose u to be e to the x, and then we'll erase that other highlight, and our dv is what's left over, cosine x dx. On the left-hand side, we'll take the derivative. So we have e to the x dx. And on the right-hand side, we're going to integrate, and the integral of cosine is sine of x. Now we can apply the formula that I've written over here on the right-hand side, and we have the integral e to the x cosine x dx. It's really helpful to write that down for this type of problem. We're going to multiply u times v, and that gives us e to the x sine x. And then we're going to subtract off v du integrated. So we're going to subtract off the integral of e to the x sine x dx. Now I want you to notice that we have an integral that looks very similar to the one that we started with. What we have to do is use integration by parts again, and here's the super important part. You need to make sure to choose u to be the same function that you chose originally, either the exponential or the trig. We chose it to be the exponential, so we're going to again let u be e to the x, and then dv is sine x dx. For the u, we will take the derivative. We have du is e to the x dx. And on the right, we have v is the integral of sine, and remember that's a minus cosine. Now let's see what we get. We can't forget this first term here, e to the x sine x, so we'll write that down. And then we're going to subtract off u times v. That gives us minus e to the x cosine x. And then we have a minus the integral of v du. So that's minus the integral minus e to the x cosine x dx. We'll wait till the very end to add our plus c. Now let's work with these negatives. We'll multiply that through. We have e to the x sine x plus e to the x cosine x. These two negatives become a positive, and then we have another negative hanging out in front. So this becomes minus the integral e to the x cosine x dx. That's a really common mistake right there, is to not keep track of those negatives properly. Now what I'm going to do is I'm going to come over here to the left, and I'm going to rewrite what our integral was. E to the x cosine x dx. Notice that our original integral turned up again when we integrated it. So all we have to do now, let's give us some more space here, is we're going to bring this integral over here to the right. So this gives us 2 times the integral e to the x cosine x dx. And this is equal to e to the x sine x plus e to the x cosine x. Now all we have to do is divide by 2, and we'll pull out our e to the x because that's a common term, and we'll add our plus c. We have the integral then, e to the x cosine x dx is equal to 1/2. We'll pull out the e to the x. We have sine x plus cosine x, and then our arbitrary constant plus c. And there's our final answer. I would put a star by this problem, and just remember, we'll go back here to the top, that this problem is one where you have to use integration by parts 2 times, and you get back the original integral. We're going to now learn about tabular integration, otherwise called the DI method, and this method can save you a lot of time for certain integrals. This method is just a visual shortcut for performing repeated integration by parts when one function, let's highlight that in yellow, is a polynomial that differentiates to 0. For example, in these two integrals, that one function or polynomial would be x squared or x cubed, while the other function can be integrated repeatedly. And that other function in these examples are e to the x and cosine x. So you have one function that integrates to 0, and then the other function you can just keep integrating. I have written down 4 steps that you can follow just to make this easier. Honestly though, after you do like 2 of these, you will completely understand how to do this without even having to refer back to the steps. We're going to go through these steps one by one as we go through our examples. In these examples, we are going to use tabular integration to evaluate the integral. Our first example is the integral of x squared e to the x dx. Let's look back up here at the steps. Step 1 says that we're going to choose the function to differentiate and the function to integrate and set up the DI table. I already set this table up, so what we have to do is to figure out which function we're going to differentiate. We're going to differentiate the x squared because that will differentiate to 0. So we're going to put x squared right under our d, and then under the I, you're going to put the function that's left over, and that is e to the x. Now let's go back up to the top and look at step 2. What we need to do is differentiate down the d column until we get to 0, and then we're going to integrate down the I column the same number of times. Let me show you what this looks like. The derivative of x squared is 2x. The derivative of 2x is 2. The derivative of 2 is 0. So you just take the derivatives until you get 0. And on the right-hand side, you're just going to integrate. With this problem, the integral is always just going to be e to the x. So we're going to put an e to the x for all of those. Now let's look at step 3 and also step 4. You can kind of combine these. We're going to assign alternating signs starting with the positive and then multiply diagonally. I'll show you what this looks like. You're going to take the x squared and you're going to multiply it by the term that's down and to the right, and you're going to put a plus by that one, and then you're going to continue this pattern down and to the right, and you're going to alternate signs, so this guy gets a negative, and then down and to the right, and this one gets a positive. And then you don't have to worry about the 0 because that term's just going to be 0. Now in step 4, let's go back right up here. We're going to add these diagonal products and include our plus c. This integral is then our first product, x squared e to the x, and that had a plus. And then our next product is going to be a minus. So we have a minus 2x e to the x. Hopefully you're getting the hang of this. And then our last product is a plus, and that is going to be plus 2 e to the x. And then our arbitrary constant c. Let's now factor out our common term. That is e to the x. So I'm actually going to write the polynomial first. So this is x squared minus 2x plus 2 times e to the x plus our arbitrary constant. And there's our answer. If you were watching this entire lecture, you might want to go back to example 3 because we actually did this problem and it seemed much harder. Tabular integration is just great for saving time for these types of problems. Let's do one more tabular integration problem. You may want to pause the video and see if you can complete this on your own. We're going to start by choosing our function that we're going to differentiate. That's x cubed. And then the function that we're going to integrate is cosine x. Now let's go ahead and let's take the derivative. We have 3x squared, and then we have a 6x, and then we have a 6, and then a 0. And on the right, we're going to integrate. The integral of cosine is sine x. Integral of sine x is minus cosine x. The integral of minus cosine x is minus sine x. And then the integral of minus sine x is positive cosine x. Let's now write down what we're going to multiply, and let's put the signs with it. We'll multiply these two terms, and that gives us a plus. These two terms gives us a minus. These two terms give us a plus. And then the last terms are going to be minus. We can now write down our answer. Our first diagonal terms are x cubed sine x. And then we have a minus 3x squared times minus cosine x. And then we have a plus 6x times minus sine x. And then we have a minus 6 cosine x plus c. At this point, it's really good to go back and check your work and make sure you did all those plus and minus signs correctly. Now we need to write down our final answer. Let's combine terms. Let's go ahead and let's combine our sine terms. And this gives us x cubed minus 6x times sine x. And then our cosine terms, we're going to have a 3x squared. Remember, we have two negatives there. And then minus 6, and that multiplies cosine x, and we have plus c. And there's our final answer. And that's it. Integration by parts is one of the most useful techniques you'll learn in Calculus 2. The more problems you work, the easier it's going to be to recognize when to use this method and then how to choose u and dv. And whenever you're faced with repeated integration by parts involving a polynomial, remember that tabular integration can save you a lot of time.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.